Continue on here and finally, I think, put to rest chapter 14. So clearly you went home, you did that exam you're instructed to do. So we will go through this example. Obviously, we've been talking about titrations and really three different types of titrations we've been talking about. We talked about at the very beginning, again, a strong acid, strong base titration. We also talked about a weak acid and strong base titration. And we finished up last time talking about a weak base, strong acid titration. And again, in the first two, we are adding the base to the acid. In this one here, we're actually adding the acid to the base in this case. And remember that regardless sort of which one you're doing, they all have a very similar sort of curve that looks like this, except for obviously this titration, which looks like that curve, but kind of starting in the opposite direction there. And that is because we're starting with a weak base there. Versus starting either with a strong acid in terms of the pH or a weak acid, which obviously would give us an acidic acid, and we're going to basic. In the case of the weak base strong acid, we're starting basic, adding acid, and obviously becoming acidic as we continue to add the acid. Regardless really of, as I mentioned, whichever titration curve you're doing, there are those four parts that are important in the titration curve. That we talked about, really how to get the pH anywhere along that curve. So there is always sort of like before you begin the titration, there is before the equivalence point, the pH at the equivalence point, and then obviously the pH past the equivalence point. As we saw with the strong acid, strong base, requires some ice tables as you start the titration. Really before the equivalence point, we're trying to figure out the concentration of our strong acid that's left over. Past the equivalence point, we're trying to figure out how much of the strong base we've added. And at the equivalence point in that strong acid, strong base titration, we have just a salt that will not go through hydrolysis. It's a neutral salt, so we expect the pH to be 7 in that type of titration. When we do a weak acid, strong base titration, at the beginning, we have a little bit more work to do to figure out the pH. Because we have a weak acid, so we have to do like a Ka type problem that we've done before. Requires obviously a nice table, molarity X's, and solving for X will get you your H plus concentration, which will allow you to get to your pH. Once we start the titration, we have a reaction between the weak acid and the strong base. That requires an ice table, and as we talked about many times up to this point, we should always do those tables in moles because we're adding volume, right? So that we get the right answer. But what will happen, as we talked about in that type of titration, is before the equivalence point, you pretty much will end up with a buffer. And at that point, after the first ice table, you can either Henderson-Hasselbalch it or second ice table if you wanted to do it at that point. At the equivalence point in a weak acid, strong base titration, you again will have really just a salt left over because, again, at the equivalence point, the moles of the acid and the moles of the base that you're adding should equal each other to 0. And basically, you'll have a salt that pretty much came from a weak acid, which means it should go through hydrolysis. And because it came from a weak acid, it will act as a base when it reacts with water, and it should take the H plus from water and produce hydroxide. So you should pretty much get a basic buffer situation. I'm sorry, a basic pH at the equivalence point. Not a buffer, obviously, at the equivalence point. It is really a hydrolysis type of problem. Really what we did when we talked about salts is pretty much the calculation that you need to do at that point. Past the equivalence point in that weak acid, strong base titration, you pretty much are just dumping in more strong base, which means you do need to do an ice table. Purpose of that ice table is pretty much just to figure out the concentration of your strong base you have left over at that point. That would allow you to get to the POH and then obviously to the pH at that point. The weak base strong acid titration, which is a curve looks like this guy here, is pretty identical to the weak acid strong base titration, except you're starting basic and kind of come in acidic. So at the beginning here, we have a we have a it's a weak base. So we would do a KB problem. And that KB problem obviously again would be with the initial molarity because we haven't added any acid at this point. That would be X's. Here you would do your ice table using the KB value. Solving for X would give you your hydroxide concentration because it's a base. That would get you to your POH and then to your pH. Just like in the weak acid strong base titration, when you do the weak base strong acid titration before the equivalence point, you will pretty much end up with a buffer again. And it's going to be more of a basic buffer at this point. And you can, after that first ice table, again, enter into the Henderson-Hasselbalch equation, or again, you could do a secondary ice table if you chose to do so. When we reach the equivalence point in the weak base strong acid titration, you once again will have a salt left over that again clearly came from a weak base, which means that it is going to go through hydrolysis. It's going to act as an acid in that case, and it's going to donate the H plus over to water, and that's going to produce H3O plus, which is why we'd expect the equivalence point there to be acidic when we have that type of titration. So again, really a hydrolysis sort of problem like we've done in the past. Past the equivalence point there on that type of titration, which is the weak base strong acid, we finish up by basically just adding a bunch of strong acid. So you need to do an ice table to figure out how much of that strong acid you have left over. And that means that you could then go into the pH equation afterwards. So again, those 4 points are really important. As we talked about, a couple of things that are important as you're doing these problems. Again, understanding maybe where you are in the titration curve can really help you understand what type of calculation you should be doing. And also figuring out the volume to reach the equivalence point is also really important. You want to make sure that you know how to properly calculate that because you might need it obviously to convert things back to molarity. The other important thing is, again, I highly recommend always after that first ice table that's done in moles, you convert back to molarity so everything's in the right units that you need. And it's just a good practice to do. So there are differences in the equivalence point of these 3 titrations. The equivalence point here should be a pH of 7, neutral. Equivalence point here should be basic, and the equivalence point here should be acidic. So depending on the type of titrations that you're doing, you know, at the equivalence point, you know, what you should expect in terms of the pH. Any questions on any of that stuff that we talked about last time? Okay, let us then look at this example that hopefully you did. If you didn't, I guess we will do it now. So let's take a look at it. We are doing a titration of nitrous acid with sodium hydroxide. So in this case here, we have our sodium hydroxide up in the burette. Here we are adding our nitrous acid, or to our nitrous acid in this case. So we have a Ka value for nitrous acid, which means that definitely should be a weak acid, and that is a strong base. So this is the type of titration we are doing, is basically a weak acid strong base. So starting with the initial solution, this would be before we added any sodium hydroxide. We would try to figure out what the pH is here. So we basically have 0.1 molar nitrous acid. And Ka value 4.5 to the minus 4, looks like. 5 times 10 to the minus 4. So because this is the only thing sitting there in our beaker before we start titration, it is going to be, obviously, as we just talked about, a weak acid problem. So we'll have our weak acid here breaking apart into H plus and NO2 minus. We're going to do our ice table here, 0.1. And again, because we're not adding volume, we're going to use the molarity, minus X, plus X, and plus X. That means at equilibrium, 0.1 minus X, X, and X. This is going to go into our Ka expression here, which is our H plus times our NO2 minus, divided by our HNO2, and put in our values. X squared 0.1 minus X equals 4.5 times 10 to the minus 4. We could assume X is equal to 0 here and sadly, because I know you did this, it is bad. It's like 6.7%. So we do need to basically distribute and solve it quadratically. So we're going to send that to the other side and do a little distribution here. That's going to give us x squared is equal to 4.5 to the minus 4 times 0.1. All right, so 4.5 to the minus 4 times 0.1. Going to give us 4.5 times 10 to the minus 5 minus 4.5 times 10 to the minus 4x. Bringing everybody to the same side, x squared plus 4.5 times 10 to the minus 4x minus 4.5 times 10 to the minus 5 equals 0. That obviously is our A, B, and C here for our quadratic. Putting that in there, going to give us negative B, which would be negative 4.5 times 10 to the minus 4 plus or minus. If we do the square root part there, that's going to be B squared minus 4 times A times C. Going to give us like a 1.8 times 10 to the minus 4. And then if we do a little square root action on it, going to give us like 1.34 times 10 to the minus 2. That is all going to be divided by 2 times 1, which is 2 in this case. Going the adding way, minus 4.5 to the minus 4 plus our 1.34 to the minus 2 divided by 2, going to get us an x value here of 6.48. We'll call it times 10 to the minus 3. Obviously, if we do the subtraction root there, that is going to lead us to a negative number, I would think. And just in case you want that negative number, that is something like negative 6.93 times 10 to the minus 3. Clearly, in this case, the negative number is not going to do us any good in this problem. And that means we can't use it because, as we can see from our table, that is what x is equal to. So that should be our H plus concentration, which means now we could go into our pH minus the log of 6.48 times 10 to the minus 3. And it looks like we're going to open up our titration here with a pH of like, I think. Any questions on that one? So again, because we are starting with a weak acid here at the beginning of this titration, we basically got to do a Ka problem to get to the pH. Put a better box around that. All right, so here, let's see what we're adding here. We're going to add 80 milliliters of our base, and we're going to add that to 100 milliliters of our acid. So 80 milliliters and 100 milliliters. So 80 milliliters of our base to our 100 milliliters of our acid. And it is still, I hope, 4.5 to the minus 4. All right. So clearly at this point, we have started titration. So we do need a reaction between those two things. So the reaction we're going to have is our weak acid will react with our strong base. Kind of similar to the calculations hopefully you were doing today. That will get you some water. And it will get you a little sodium nitrite in this case. A little double displacement type reaction, right? That way, this guy going that way. Right? All right. Clearly, since we started the titration here, we got to do this in moles. So that is what we want to do. So we're going to convert our volume into liters. So for our For our first one here, we would have 0.1 liters times 0.1 gives us an opening moles of 0.01 moles. And that again is what we're starting with here. Our base 0.08, which is 80 milliliters converted to liters times 0.1 gives us 0.008 moles. And that is what we're adding. And we have 0 of that. Are we before the equivalence point, at the equivalence point, or after the equivalence point? We are definitely before the equivalence point. What we are adding is less moles than what we started with. So we are here before the equivalence point. That also should help you know where we should end up with on this thing. That means at this point, the sodium hydroxide is the limiting reagent. Again, just logically speaking, take the smaller number, even if you don't want to, take the smaller number, and you'll be all right. We will do this. That means that at the end here, we will have 0.01 minus 0.008, going to give us 0.002 moles. This is going to zero out, and we would have our 0.008 moles. Now that we did this first table here in moles, we are going to convert back to molarity. We're going to use our total volume at this point. So we have 100 milliliters of the acid we started with. We added 80 milliliters of the base. So that is going to be 180 milliliters is our total volume. But remember, it does need to be in liters. So we want to divide here by 0.18 liters divided by 1,000, right? And if we do that, we got it's not on my calculator, 0.002 divided by 0.18. Going to give me a 0.0111. And over here, we will end up with 0.0444. Any questions so far? By knowing that I am before the equivalence point, right? In this type of titration, I should end up with what thing? Should end up with a buffer. And if you're not sure of that, you could look at your ice table. That is sodium nitrite, and that is nitrous acid. Those two things are related to each other. And there's the buffer that we should expect by knowing that we are before the equivalence point. So again, if you kind of know where you are at, you should know what you should end up with. So if you end up with this table not in a buffer situation, you did something wrong. Yeah, so it's a good way to check yourself. Because it is a buffer, we could go into the Henderson-Hasselbalch equation, might be the easiest. So pH is equal to pKa plus the log of the base over the acid. We need a little pKa value minus the log of the Ka, which is 4.5 times 10 to the minus 4, minus the log 4.5 to the minus 4. That's going to give us a pKa value of 335. So putting that in, plus the log, once again, we want to make sure we get the base up on top, and that should be this guy. Acid on the bottom, which should be this guy here. What we got there? So 0.0444 divided by 0.0111. There we go. A little log action of it. One more. Whoa. Come on, calculator. There we go. All right, log. And we're going to add it to 335. Looks like maybe a 395 there would be our correct one, hopefully. Any questions on that part of it there? Also making some sense since we are adding sodium hydroxide in our titration, so we should expect the pH to start to climb. So we started at 295. We've now climbed up to 395. We moved the whole 1 unit in pH here. Yeah. Any questions on any part of that there? All right, then let's take a look at part C. So we did B. So at C, we're looking for what is the pH at the equivalence point. So let us talk about that then. So at C, the pH at the equivalence point, once again, we have our 0.1 molar HNO2, and we have 100 milliliters of it. We're adding 0.1 molar sodium hydroxide. All right, and our Ka value 4.5 times 10 to the minus 4, I believe. So we're going to still have our reaction. So that's going to be our HNO2 plus our sodium hydroxide, going to give us the same reaction, which is our water and a little sodium nitrite. Once again, here we do want to do moles. So we're going to do 0.1 times 0.1 for our HNO2, gives us 0.01 moles. We do need the moles of the sodium hydroxide, so it might be helpful to figure out the volume needed to reach the equivalence point. But even if you're not sure how to do that, the one thing you should know is because we're at the equivalence point, the moles of sodium hydroxide should be what number? Be the exact same number. Yeah. So we definitely know that for sure. So that gives you, again, two ways that you can really kind of figure out what the volume of sodium hydroxide you need. One way is obviously now that you know the moles and you know the molarity of it, you could solve for liters, which would be moles divided by molarity, which in this case would be 0.01 moles divided by our molarity of 0.1 moles per liter. And if you do that, 0.01 divided by 0.1 gives us 0.1 liters, which is 100 milliliters to get there. The other way that you could get there is over here, M1V1 equals M2V2. That would be 0.1, which is our acid. 100 milliliters of our acid equals our 0.1 molar of our base and our V2. If you solve for V2, that is what you will get there. So you can do M1V1 equals M2V2 because it is a one-to-one relationship. Remember that if it's not a one-to-one relationship, you shouldn't use that because you'll get the wrong stoichiometry part. But if it is one-to-one, you can use M1V1 equals M2V2. Or again, you could do like we did earlier there, use just the molarity and the moles that it should be, and you can get the volume. Any question on how to get to the volume in either of those cases? All right, so this should be 0. And at this point, we really can't choose the wrong one as it is the same number. So it's got to be this for the change. That means we have nothing here and nothing there, which is what we would expect to happen at the equivalence point, 0.010 moles of this guy. This is why at this point, it's important to figure out how much base you need, because now we need to divide by the total volume. And the total volume in this case actually is 200 milliliters, not 100, right? So we got to get that 200 milliliters. And it's 100 from the base and 100 from the acid that we started with, right? Gives us our 200 milliliters of total volume at this point, which does need to be converted to liters, which would be 0.2 liters. So that's going to be 0.01 divided by 0.2, going to give us 0.05 molar. Any questions on that ICE table? Yeah. That's actually what I was going to say next, and it does go through hydrolysis. So it will go through hydrolysis, and this is what we should expect to happen right in this titration because we're at the equivalence point, and that salt basically came from our weak acid, right? So you are correct at this point. It will go through hydrolysis as that is the only thing that is left. And the reason we need to get this back to molarity is for the next part of the calculation, we need to be in molarity and not moles. So that you have the right answer. So it does. And that's because the only thing left at this point is a salt that will break apart into sodium ion. and nitrite. And once again, the sodium is neutral. It is the nitrite that comes from this weak acid that will go through hydrolysis. So we do need a second ice table like we talked about, which will be our salt plus the water. And once again, understanding that it does come from a weak acid means that, frankly, this will be a base. And that is what it's going to do when it reacts with water, which means it's going to accept the H plus in this case. And when it accepts the H plus, it will always make where it came from. And it will make our hydroxide, which again, we should know now that the pH here should be basic because we're creating OH minus at this point. We're going to take our equilibrium concentration here. That is now going to become our initial concentration at this point, 0.05. And the rest of this will be zeros and x's. So minus x, plus x, plus x. That means at equilibrium here, 0.05 minus x, x, and x. At this point, this will go into our K expression, which will be our products over our reactants. By the way, what type of K is this? This is a K. It is a KB because there's hydroxide. So that also means that we need to convert our Ka into our KB to have the right value there. So our KB in this case would be the KW divided by, if I put a 14 there, divided by our Ka, which was 4.5 times 10 to the minus 4. And if we do that, it's going to give us like 2.2 times 10 to the minus 11. All right, so I'm going to put my equilibrium line into that and solve for x. I'm going to actually flip a page here as we get to the bottom. So I'm going to go and pop that stuff into my KB expression. And that would give us x squared over, it was 0.05 minus x equals 2.2 times 10 to the minus 11. At this point, we can assume that x is equal to 0. That's going to give us x squared divided by 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply this to the other side and also take the square root. So we're going to take that times 0.05, a little square root action, going to give us an x value of, we'll call it 1.1 times 10 to the 1, 2, 3, 4, 5, 6 minus 6. We do want to check it, so we'll divide it by 0.05. We'll times it by 100, and it's nowhere even near 0.1%. So we're all good on that. So this would equal, though, if you remember, if we come back to our ice table, that is not going to equal the H plus, but it is going to equal the OH minus. And that is what that guy will equal. That's going to allow us to get into the POH minus the log of 1.1 times 10 to the minus 6. Going to give us a 5.96 to get to the pH. We then need to subtract 14 to do that. So minus 14, 804 looks like, which is basic. And again, what we should expect to happen at the equivalence point in this type of titration. Any questions on that? Yeah. So in this type of titration where it's a weak acid and a strong base, it will always produce hydroxide. And that's because the salt always comes from the weak acid, which means the salt part will always be a base, which means it will always accept the H plus, producing the hydroxide. Now, if you did the weak base one with the strong acid, it would also go through hydrolysis. But because the salt in that type of titration comes from a weak base, the salt will act as an acid and donate the H plus over and make H3O plus. So always, no matter what the weak acid is in this type of titration, and strong base. As long as it's a weak acid, strong base should always produce hydroxide because of that, and it'll always be basic. Yeah. Other questions? All right, so also makes sense, right? We're not going backwards in our pH here. So we were at 3 something, now we're at 8, right? We're at the equivalence point, and now you're not going to stop because, hey, you still have some sodium hydroxide in the burette. So why not do part D here, which is what happens where we add 105 milliliters of our base. So continuing on here. So part D, 105 milliliters of our base is added still to our 100 milliliters of our acid. So once again, we're going to do our equations. So some nitrous acid, some sodium hydroxide, some water, and a little sodium nitrite. Once again, as we've been doing, we're going to do some moles. So our initial moles here, what we are adding, pretty much going to be the same. So we're starting with this guy of 0.01 moles. For our base, 0.105 liters times 0.1 gets us 0.0105 moles. And this is what we're adding. And this is obviously 0. We are definitely past the equivalence point. And remember that as we go past the equivalence point in this type of titration, you're pretty much just dumping base in there. And what that means is there is a switch that occurs. And this now is like our limiting reagent. And this guy is our excess reagent. So the change part here is actually going to be the acid, as you do not have enough of it basically to handle what you're adding. So you would then take minus the amount of the acid in this case. Remember, you cannot have a negative number, so don't do the other. Yes. All right, so you got 0. We got a little 0.0105 minus 0.010. 0.0005 moles and 0.01 moles here. Our total volume at this point obviously is just adding these two together. That's going to give us a total volume of 205 milliliters. So we'll divide this by 0.205 liters. That's going to give us 0.00050 divided by 0.205. And that's going to give us 0.00244 molar. And 0.01 divided by 0.205 going to give us 0.0488 molar. So if you're not sure what's going on, which you should kind of know what's going on just by knowing you're past the equivalence point, but if not, you could always look at your ice table. So we got this guy and we got that guy. First off, is it a buffer that you see? It is not a buffer, even though there are 2 numbers there, right? We basically have 2 bases in this case, right? So as we saw in the previous part when we were at the equivalence point, the salt there will go through hydrolysis. It will act as a base. So we got this base here. And we also have definitely this guy, which is a strong base. So as you know, past the equivalence point between these 2 bases, obviously the sodium hydroxide is a much stronger base than the sodium nitrite. It doesn't need to go find water to produce hydroxide. So this is the part where we ignore the contribution of the salt and we look at really just the strong base's contribution, which basically means this should be our hydroxide concentration. So that's going to allow us to calculate the pOH, which would be minus the log of our hydroxide, 0.00244. Looks like a 261 as our pOH, and obviously we do need to get to the pH here. If by some chance you thought that was the pH, it should not make sense to you. So this would be a much better one, maybe 1139, which is definitely basic as the equivalence point where it was at 8. And here, by just going to 5 more milliliters, we jumped to a pH of about 11.4, right? So we jumped up about 3 pH units by adding about 5 milliliters of solution in this case. Question on any parts of those titrations? So again, if you understand where you are in those titrations, you should understand the type of calculation you're doing. And again, it can help you maybe not make some mistakes if you sort of understanding that. Question on titrations in general. All right, to finish up this chapter here, we're going to talk about acid-base indicators. So as we've talked about before, we do use indicators to help us determine, where we should typically stop in a titration. And most titrations that people do, they don't necessarily make the entire titration curve like we will do in the next experiment. But a lot of times they do want to stop at the equivalence point. So you need some type of visual indicator usually to tell you, hey, you should lay it up. And those are really acid-base indicators. Acid-base indicators are frankly just like weak acids, and they have a protonated form, and this is sort of equivalent. That's HIN is indicator basically. So it has like an H plus attached to it, and then it has the deprotonated form of the indicator, which has lost the H plus, much like a weak acid. And really depending on sort of the ratio of sort of the protonated part of the indicator to the deprotonated part, as to what color you would see. So if kind of you have more of the acid part of the indicator in there that has the H plus still on it, you'll see the color of the acid solution. And if you have more of the base part, you'll see the base color. Most indicators do work over a specific pH range. And typically what you see is sort of a gradual or color change as you move up the pH sort of range. You do want to choose one where you can visually see a color change near your equivalence point, right? You do not want your indicator to change color way before your equivalence point, because frankly, it's not really doing its job, right? Its job is to tell you to stop. If it changes way before your equivalence point, you're going to stop way before your equivalence point and not be correct. So here are some examples, obviously, of some different ones. You can see, for example, we got some yellow to a green to a blue. Here is phenolphthalein, which is a common one that we use. And again, it works from like a pH of 8.3 to 10-ish. And as you can see, until almost the highest part of 8, you start to see a little bit of pink starting to come in. And again, it gets darker pink as you go through there. So you always want to choose one where you can visually sort of see that color change. So here's a table of some indicators and their colors in acidic solution and basic solutions and the pH range at which they work. So if we did a titration of nitrous acid with potassium hydroxide, which ones on this list would be perhaps a suitable indicator to use in those titrations? So take a moment, look over the list, see which one do you think would perhaps work good. Let's take a look. So first off, HNO2 is what type of acid? It is a weak acid, it's the one we just did, right? And KOH is a strong base, right? Which means we should know just from that combination at the equivalence point, should it be acidic, neutral, basic? It should be basic, as we were just talking about, because you're going to have that salt that will go through hydrolysis and produce hydroxide, right? So here we have thymol blue, which works between like 1.2 and 2.8. That means it's going to change color way too soon for you. This is bromophenol blue, 3 to 4.6. Also a little bit too soon for it to change colors. Too soon to change colors here, here, here. This guy also probably a little too soon to change colors, because at 7.6, it probably has already changed color, which means you're way before basic at that point, and you're not going to probably be able to see it. How about cresol red is a possibility, right? That is definitely in the basic range, so that might be good. And our good friend phenolphthalein, which works between 8.3 and 10, would also be good as well. And if you wanted to really narrow it down, you could do a calculation like we just did and have a pretty good idea as to where it should change. And you could pick one that obviously would dial it in pretty good. So probably the best choices off of this list would be these two. The other ones would be terrible choice. Which ones would be good if I did a weak base with a strong acid? The equivalence point should be acidic, basic, or neutral in this case. Should be acidic, right? Which means the two that we just chose would probably not be a great choice. Probably this one would not be a great choice. So depending on what weak base and acid you're using, more of the acidic ones would obviously be a much better choice. And again, you could do a theoretical calculation and really narrow it down to one that would be the most appropriate to use in that situation. Question on that there. Yeah. Yeah, because basically this is the pH range that really where it changes color. So even though it says basic, it's going to be pretty much by 2.8 pH, going to be changed to that color. And it will stay that color all the way kind of through, which means if your equivalence point, say like the one we just calculated was 8 point something, right? If it changed around a pH of 2.8, that's like way too soon to stop, right? And that will not give you a good indication of where you should stop. Yeah. So you definitely want to make sure you choose one where you can actually see the color change around the equivalence point. And again, just like phenolphthalein pretty much is at 8.3 to 10-ish, is pretty much colorless in this range, right? So there is no color, which means if you did this titration where the equivalence point is acidic, you're really not going to see a color, right? And by the time it does change color, it's in the basic range, which means you're way past your equivalence point at that point. Or, you know, or it would actually, maybe if you were doing that titration, it actually would go from pink to colorless around 8.3, which is way before your equivalence point as well. So you want to make sure that you do choose one that you will be able to see that change. Any questions on indicators or how to properly choose them? So they're not all the same. They're not all equivalent. And that's why for probably most of the titrations you've done previously, they always give you kind of phenolphthalein because they have you do a titration of a weak acid, usually like vinegar, and a strong base. And that's usually why they would choose that one. And even with HCl and sodium hydroxide, by the time it changes, it will still be in that vertical rise. So even though it's way past 7, it will still be okay to use. But probably a better one for, say, a strong acid, strong base would be something maybe in this range where you might be able to kind of dial it in a little bit more. All right, that wraps up chapter 14. I can't believe it. All right, then we should go off to 15 maybe before we change our mind. So chapter 15, we're going to talk about some more equilibrium, surprisingly. We're going to talk about what's known as KSP, and we're going to talk about what is known as KF. And KSP is what is referred to as the solubility product. It has a lot to do with the solubility. So our good friend solubility rules might be good things to know. Also, it is really, as we'll talk about, the equilibrium constant for things that are like insoluble, right? Things that are pretty much insoluble is kind of what we're doing. KF, as we'll talk about, is really what are referred to as complex ions. So that is the formation constant and is used for complex ions. So these are two different types of things. And they're actually sort of opposites of each other in terms of the values that we see for the Ks and sort of how we deal with a lot of these sort of calculations. So let us get into some of this here. We're going to start with KSP, which is the solubility equilibrium. Now, KSP, as I mentioned, is essentially the equilibrium constant for things that are insoluble. So based on solubility rules, there are certain ionic compounds, right, that if you put them together should make a solid. Like if you put together silver and chloride, right, and make silver chloride, you get a solid that forms. There are things that are soluble, right? If you take sodium and chloride together, it is soluble. And that's because chlorides, bromides, iodides, right, they're soluble in everything except for silver, lead 2, and mercury, yes, 2. So that's those solubility rules, like nitrates are soluble in everything. Yes. So those type of things. So even though something is technically based on solubility rules, insoluble, everything has some degree of solubility. So even things that are typically we think of as This thing is a solid. It's going to make a solid. It's not going to dissolve. Some of that solid will dissolve into ions in solution. So even if it's a really, really small amount, it will still be able to dissolve. So something like silver chloride, which we normally think of as a solid, will always still break apart a little bit in solution into the ions that are there. And we can write a equilibrium constant for it, which is our products over our reactants. And this is what is known as the KSP, which stands for solubility product. And it is our products over our reactants. And normally, right, we do not put solids in the equilibrium expression. And that is why we don't see it here. It is just really our products in this case. And that is typically how KSP reactions are always written: solids on the left to ions on the right, basically. Which means when you write the KSP expression for pretty much all reactions, you pretty much just have the products. And we still do the normal things that we do. If you have some type of coefficient, it still becomes the exponent and stuff like that, but they're typically just the products. So if we wrote the KSP for this guy is concentration of silver times the concentration of chloride. If we had magnesium fluoride here, it would break apart into a magnesium and a couple of fluorides. And again, this is a solid, so not included, but we do include, once again, our coefficient. So that is going to be the concentration of magnesium times fluoride squared. Same thing with our silver carbonate. We got a coefficient there. We do need to make sure we include it when we write the KSP expression. And with something like calcium phosphate, we actually have two coefficients. And again, they both need to be incorporated into it. KSP values, as we will see, are frankly relatively small values. So when we have KSP values, they typically are small values. And because they are a KSP, which really means that they are still a K value, when you have a small value of K, you mainly have reactants or products. Yeah, so that's why these things are insoluble. You have really small values of K, which means for the most part, everybody's hanging out over here, but a little bit of these guys are still going to break apart. And that's why we will see very small values, typically for KSP values. So like minus 32 or something like that, or minus 12 or 16 is the exponent, a really small sort of value. And that's because these things are typically insoluble, which means they stay together. And that means that they stay on the reactant side. But again, a little bit of it will break apart. One way that we could use KSP is to figure out whether or not, if we put two ions together, would we get a precipitate to form or not? Now, based on solubility rules, it may tell you that, hey, if you put these two things together, you will get a solid that forms. But there are a lot of factors that actually affect whether or not, for example, some type of solid would form. And we're going to talk about these things. And one sort of thing that affects the possibility that an ion solid would form is concentration of the ions. So if you don't have the right concentration of the ions in solution, even though your solubility rules tell you you should get a solid, you won't see the solid happen. Other things that could affect it that we'll talk about in this chapter is things like pH. So if you don't have the right pH, you may not see the solid form in terms of the environment. And things like common ions also can affect the solubility of something. So even though we sort of think about it in like Chem 50 in the first semester, we sort of think about, oh, these are like for sure always the rules, no matter what the situation. When we learn those solubility rules, there's a lot of factors that could affect the solubility of a substance as to whether or not you actually see the solid form or not form. And again, we'll go through each of those and see how they affect them. But one thing that we can sort of calculate is if we do know the KSP value and we do know really the concentration of our ions in solution, we could calculate Q. And if you remember, Q is the same Q that we used in the equilibrium chapter, and that is the reaction quotient. And if you remember, Q is calculated the exact same way as you would calculate K. So if I wanted to calculate Q for my silver chloride, it would be the concentration of silver times the concentration of chloride. So remember that Q is basically calculated exactly the way that you calculate K. If you calculate Q and it is less than the KSP value, you could think about it going opposite of the way it's pointing. That means it will go to the right-hand side of the equation, and the right-hand side of the equation is all ions that are aqueous, and that is an unsaturated solution. Unsaturated solution is a solution where you have not hit the saturation point, which means if you put more solid in there, it should continue to dissolve, right? And it should continue to dissolve until you hit the saturation point, which is a saturated solution, right? And a saturated solution is a solution where you've hit exactly at that temperature the maximum amount of solid, right, that you would be able to dissolve in that solvent. And that is what happens when you get Q is equal to the KSP. You have a saturated solution, which technically means you still won't see a solid probably, but you're right at the point where if you just put a little bit more in, you will see a solid. So you're like right there at the tipping point to see a solid. If you calculate Q and it is greater than the KSP value, that means you have a supersaturated solution. And by the way, it goes opposite of where that points to, which would put you to the solid side of the equation. And you would expect to precipitate to form. Supersaturated solution is one where you got like way too much solute dissolved in there, so much it wants to come out of solution as a solid. They used to do an experiment with sodium acetate. You make a supersaturated solution by dissolving a lot of solid in, say, water. You heat it up, which allows a lot more of the solid to dissolve. Then you cool down it. And when you cool it down, the solubility comes down and you end up with a solution that has way too much solute dissolved in it. It's so unstable that if you just knock it like on the table, all the solid will come out of the solution because it has way too much dissolved in it. I know that because I did that yesterday in an exam in a lab. I did actually knock it before I added anything, and just all the solid just came out of the solution, stuff like that. So those are really good things to know. We use Q and K like we kind of did before to help us understand whether or not we would expect to precipitate or not. So these are some KSP values. It's clear you should memorize. No, I'm just kidding. It's in your tape. It's in your book. But what we will see in a lot of these is there are a lot of really small numbers. So like minus 28, minus 45. So for the most part, the KSP values are really small values. And if you see a KSP value for something, then you can pretty much safely assume that that thing is a solid that will break apart into its ions. And again, the solid will always be on the reactant side. So there's kind of two routes to KSP type problems that we come across. And there's two types of solubilities that we oftentimes look at. One is sometimes referred to as the molar solubility, which is, I guess, a fancy way of saying molarity. And that is the moles per liter of a solute. So the amount of moles of a solute that you can dissolve in 1 liter of saturated solution. And then there's just sort of blanket solubility, which is usually how many grams per liter you can get to dissolve of that particular solute. A reminder, right? The solute is the smaller part of a solution, right? The solvent is the larger part of a solution. Both of those things together make a solution, right? The solute and the solvent. The solute is always the name of the solution, right? So if you have a sodium chloride solution, the solute is sodium chloride. So in these type of problems, you may be given the solubility of a compound, and it may be given to you in any type of unit. But ultimately, what you want to do is once you have the solubility of that compound, you do want to convert it typically into the molar solubility. So you want to get it to moles per liter. So if you're given to you in grams per liter and you wanted moles per liter, what is the thing that allows you to do that? What do you need to do that conversion? What is really the only difference between these two things? Grams in. So how do we convert grams to moles? Yeah, you need the molar mass is the one that ties those two together. Yeah. So the molar mass from the periodic table, which is grams per mole, is the thing that ties those two together. Going, depending on which way you're going, obviously, is what you would do with it. But that's a very common thing that you need to use in these type of problems, is to get to the molar mass and go from grams to moles or moles to grams. Once you have that, you want to convert the molarity of the compound into really the molarity of each of the individual ions, and then that would allow you to go into the KSP expression and solve for what the value of the KSP would be. Now, typically speaking, if you understand how molarity works for the entire compound and the ions that come from it, you technically don't have to do an ice table for that type of problem. You can do an ice table for that type of problem as well, and it might help you not mess up where a lot of people mess up, but you don't necessarily have to do it. The second sort of path is you're really just strictly given a compound and they're like, what is the solubility of this compound? And really the only piece of information you're given is the KSP value. You're not given any concentrations or anything like that. You just basically have the compound and it's like, hey, what is the solubility of it? Be it the molar solubility, the solubility in grams per liter. That sort of approach, you do have to do an ice table typically to solve it correctly. And we'll talk about how that ice table is a little bit different than some of the ice tables that we've done before, but you typically do have to do an ice table. So doing this calculation, you should do an ice table. Doing this calculation, it is sort of optional, but it can be helpful to do one for that type as well. All right, so let us talk about how to do this, and we'll go through this one here together so we can see how it works. We want to know, what is the solubility of silver phosphate at 25 degrees Celsius? I'm sorry, I could read that wrong. The solubility of silver phosphate at 25 degrees Celsius is 1.6 times 10 to the minus 5. What is the KSP of it? I don't know why there's a dramatic pause between these things, but they're just there for effect in this case. All right. So in this case, we actually have the molar solubility given to us. So this is one where we technically wouldn't necessarily have to do an ice table, but I'm going to do the ice table so you can kind of see how the calculation works for ones where you should do it. So if we were going to take more of an ice table approach on this, we would start with our silver phosphate here together. And because it has a KSP value, we know that that guy's going to be a solid in this case. And that means it will break apart into the proper number of ions, which is 3 silver ions in this case, and a phosphate. That also means that our KSP expression here would be the concentration of silver, and I need to cube it because of the coefficient. And I would times it by the concentration of phosphate, which I don't have to do anything to because the coefficient is 1, and that equals basically what we're looking for in this particular problem. Any questions on that? So if we were going to take this ice table approach, we would do an ice table, and frankly, we would have 0 this guy and 0 this guy to begin with. I'm not going to do anything with the solid because it's not included in anything, right? So I'm not really going to do anything on the solid side here of the reaction because it doesn't go into the equilibrium constant, doesn't really do much. But normally in this case, right, we assume that the reaction is heading in this direction, which means, again, the left-hand side would be our minuses. The right-hand side would still be our pluses. Now, in solubility type problems like this, maybe because they got bored, they use a different symbol or letter than X. If you want to use X, you can. They actually use S instead of X. And S stands for molar solubility. That's probably why they use it. It tells you what the molar solubility is. If you want to use X, you can, but we'll use S here. And it works the same way. We still need to take the coefficient into account. So that should be 3S. And this would be plus S, right? Any questions on that there? Coming down to equilibrium, we would have 3S and S. All right, now at this point, what we would do is we will put this into our expression just like we have done before. So that would tell us that the KSP is equal to our silver cubed times our phosphate, and putting that value in would get us 3S cubed times S equals, again, the KSP. Now, in this situation, if you actually were given the KSP value, you would use the KSP value and you would solve for S, right? And that's what you would normally do. If it was a different type of problem where all you had was a KSP, you would use it just like we would do for X and solve for X, you would solve for S, and that would give you the molar solubility. The deal on this one is we don't have to worry about figuring out the molar solubility because frankly, they gave it to us right here. That is the molar solubility. So that really is our S for this particular guy. That means we could just put that value into here and we should have our answer. And if we did that, that would be 3 times 1.6 times 10 to the minus 5. We still got a cubit times 1.6 times 10 to the minus 5. And if we do that, there 3 times 1.6 to the minus 5, we're going to cube it and times it by 1.6 to the minus 5. That's going to give us a KSP value of 1.8 times 10 to the minus 18. It is still a K value, which means it has no units, and it's a small K value, which makes sense. That means that pretty much most of this is still staying together as an insoluble solid. Question on that. Now, why I would recommend perhaps you still take the ice table approach in this type of problem is it is a very common error that a lot of people make, which is I did the 3 here. I still have to do the 3 here. Or they do the 3 here and forget to do the 3 here. It's a very common sort of error that people make. So if you kind of visually just kind of see it, you know, okay, I got the 3 there. I still have the 3 there. You know, that's the way I probably should do it. Now, the other way you obviously could do it is if you understand, again, how molarity works in this particular problem. Because this guy was 1.6 times 10 to the minus 5, it is a 1 to 3 relationship. You would times this by 3 times 1.6 to the minus 5. That's a 1 to 1 relationship between that and phosphate, which means this would be 1.6 times 10 to the minus 5. And then those would go into here. Yeah. So the ice table is just walking you through the fact that you need to multiply it by 3 and stuff like that. So you hopefully won't forget to do so. But if you understood that's how you get the molarity of each of the ions, you could just do that and then go into the KSP expression, which is the same deal. Question on any part of that there? All right, I tried one, you try one. Here we go. What is the solubility of silver chloride? In grams per liter, the KSP is 1.6 times 10 to the minus 10. And silver is like, I think, $1.7.9, I hope. Yeah, this is still ish. And chlorine is 35.45. All right. Give it a go, see what you come up with. Okay, let's take a look at this one. So we're looking for the solubility of silver chloride. Again, the only thing given to us is a KSP value, which, by the way, you may have to look up in tables. They may not be given to you necessarily in the problems. And there should be a table, obviously, in your book. So in this case, we definitely need to do an ice table, and we would start with our silver chloride. We do know it should be solid because I see a KSP value. It will, though, break apart a little bit into silver ions and chloride ions in this case. Our KSP here would be the concentration of silver times concentration of chloride, and that would equal our 1.6 times 10 to the minus 10. So in this situation where we're pretty much not given anything other than this KSP, we just roll through an ice table. So this is going to be 0 and 0. Our change would be plus S and plus S in this case. That means at equilibrium here, we would have S and S. Once again, we're not going to worry with this guy because he's a solid. Any questions on the ice table here? So kind of similar to what we've done before here, we're going to try to solve for S, and we're going to take those and put them into our KSP expression. And if we do that, we end up with basically S times S is equal to 1.6 times 10 to the minus 10. That then gives us basically S squared, 1.6 times 10 to the minus 10, and taking the square root there. of that will get us, I don't know, 1.3 times 10 to the, I don't know, 1, 2, 3, 4, 5 minus 5. Any questions on that so far? That, by the way, is the molar solubility or concentration of silver ions in that solution, right? This is also the concentration of the chloride ions in that solution. And this is also the molar solubility of our silver chloride as well. So this would be the molar solubility of our silver chloride. The whole thing would also be 1.3 times 10 to the minus 5 molar. If you're not sure how that works, it works like this. If we put that number back into here, it is a 1-to-1 relationship between those two, which means it'll be the same number. If you put it back into here, it is a 1-to-1 relationship. It will be okay. Even if it's not a 1-to-1 relationship, you would divide out the numbers. So typically speaking, when you solve for S, that is your molar solubility of your compound together. So it's the whole thing in most cases, okay? So because of that, that basically is 1.3 times 10 to the minus 5 moles per liter of silver chloride is basically what we got going on there. So as we just talked about, we're looking for grams per liter. So we do need the molar mass, which hopefully I read right off the periodic table there. So we're just going to add these together. In this case, that's 107.9, I hope. 3545, about 143.4 grams per mole. Using that as our molar mass here, 143.4 grams per mole of silver chloride. The moles will cancel. And that will get us 0.0019 grams per liter is the solubility of silver chloride in water. Yes. Any questions on that? Is that a lot of silver chloride that you could dissolve in a liter of solution? It is not. It basically means you could dissolve 0.002 grams in 1,000 milliliters of water, which is not very much. That is why we normally consider silver chloride to be insoluble, right? So, but it also demonstrates the idea that even though it's technically insoluble and pretty much most of it still stays together as a solid, there is always just a little bit that is able to break down even a super small amount of a whopping 0.002 grams, right? Any questions on that there? All right. I think we'll lay it up there for today.